Our first speaker is Titus Northcurt. He's a theoretical condensed matter physicist and associate professor at the University of Zurich. His research covers many aspects of topological states of matter, and he also has interest in machine learning, quantum computing, and numerical methods for many body quantum systems. He obtained his PhD from ETH Zurich in 2013. At that time, he also worked at the Paul Scherrer Institute, and he was a postdoc at the Princeton Center for Theoretical Science before joining the University of Zurich as a professor just 5 years ago in 2016. And the title of his talk is Topology in Quantum Matter Beyond the Rules of the Game.
Okay, is this live? Yes, sounds good. Very good. Thank you very much for this kind introduction and these nice thoughts. I'm very excited and glad to be here for this workshop. It's also my first scientific event in a long time with a real audience. It feels a little bit like a TV show where you have like the studio audience and then there are the people watching on the screen. So I encourage you, actually, I don't know, can we monitor the chat in case somebody has questions or so? Encourage you to just interrupt me if there's anything about the understanding of the talk, you know, just go right in there. All right, good, let's get started. Topology in quantum matter beyond the rules of the game. I want to basically take you on a little journey on how we think as theorists about fundamental concepts in quantum matter. And I'm actually almost spare my first slide because that was already very nicely covered in these introductory thoughts. So what are the big challenges that we face in rethinking computing nowadays? And that is, I guess, the biggest question that quantum matter research is focusing on. Well, the challenge is that the traditional way of doing computing, where we have separate memory and computing parts in our system, that is basically a thing of the past, and it's not working very well with the demanding computations, AI and ML type of applications that we now have. And on the other hand, we want to rethink computing because we want to harvest the power of quantum mechanics for computing. So we want to think about quantum computer and quantum simulator applications. And of course, all of this comes together in the concepts of machine learning, neural inspired computing technology. Now, all of that sounds really cool, but of course, as a community, we have to come up with a hardware foundation that makes all of this feasible, or many different hardware foundations depending on the specific needs. And also, we probably want to harvest novel physical effects. And this is basically how I understand the mission of our community. And my angle on contributing to this mission is looking at topological states of quantum matter. And this in itself can have many different aspects. So we can look at the topological band theory, we can look at low dimensional nanostructures, and also incorporate interacting and correlated phenomena in quantum matter, as well as to an increasing amount non-equilibrium and driven systems. All right, so from this angle, I want to now first take you on a very quick overview tour to what has been achieved in the last, let's say, decade and a half on topological quantum matter research. And this tour is heavily biased and it's definitely selective, so don't be disappointed if certain favorites of yours don't show up. But I want to base it on systems or ideas that came out of theory, considerations that are based on theoretical concepts, and then found their way into experiments, and by now in beautiful experimental realizations. So one thing that's common to all type of topological states is a bulk boundary correspondence. That means that we have a bulk of a system, which could be actually rather boring looking, an insulator, for instance, and the actually interesting physics happens at the boundary where something anomalous happens, some quantum states, for instance, that could otherwise not be realized in this dimension of the boundary. And the first instance that has to be discussed here is the anomalous quantum Hall effect. Somehow lacking a pointer. Let me try to move my mouse pointer over here. Okay, very good. The anomalous quantum Hall effect, which came from, of course, 80s research in integer quantum Hall physics, let's say, and there we have by now very nice material realizations, both in actual 3D crystals milled down to few layers, as well as in atomically thin materials like twisted bilayer graphene. Another big achievement is intellectually the idea to extend this to time reversal symmetric systems, and that is when we talk about topological insulators in 2D and 3D. And again, here we have now the quantum spin Hall effect at 100 Kelvin, so at much higher temperature as a clear transport signature in tungsten ditelluride, or we have these beautiful Dirac cones on the surface of topological insulators, which are their anomalous topological surface states. And again, theoretical ideas were foundational, then came a lot of very important experimental work, and we have now quite nice realizations. And then the journey went to semi-metals, where topology is actually inherent in band touchings, where, for instance, two bands meet in momentum space of a semiconductor, let's say, and these band touchings can be protected against perturbations. And then we speak, for instance, of a Weil semi-metal, and that has been, conceived theoretically already long time ago, but only recently we really found nice experimental verifications. 2015, the first ones, but then also here we have. Yeah, hi, Niels over there. very nice experimental manifestations of the, for instance, the boundary states here, which are Fermi arcs. And another thing that I contributed to the field was this perspective on higher order topological systems, where not only the surface states are interesting, but actually the states on hinges of a crystal are topologically protected and carry some non-trivial character. And there we have also nice materials now, bismuth bromide, for instance. Finally, a topic that I'll touch upon later in the talk, fragile topology. That is something we also see in twisted bilayer graphene, and it's only recently been theoretically conceived. All right, so with this, I just wanted to make the point that much of the research in topological quantum matter is driven by theoretical concepts, which are by themselves very beautiful, but then, of course, finding a suitable platform in quantum materials where they are realized is a tough job, but we've been succeeding in many cases as a community and found beautiful realizations. Now, going back to my title, Beyond the Rules of This Game, I want to basically suggest that going forward, making new discoveries along these lines, we have to rethink by what standards did we judge something here as topological, as interesting quantum matter, and how can we go beyond by asking whether these rules are meaningful or should be altered. How can we find other interesting effects? And about the states that I've been mentioning, two things stand out. So they are all defined for zero temperature phases of quantum matter, which are mostly gapped Hamiltonians, and we talk about the occupied bands of these, or the occupied states of these Hamiltonians. So in that sense, we implicitly talk about energy conserving systems because we talk about band structures in Hamiltonians, and we only really interested in empty states. Yeah, sorry, in the occupied states, and we kind of throw away information about the empty states, the conduction bands. And basically, the purpose of my talk, to a large extent, is to give you a flavor of how, as a theorist, we are thinking of new principles and basically work towards the new manifestations, new physical effects by asking whether these rules of the game are proper ones or whether we can extend and go beyond them. And I want to do that by showing you three different systems. One is a non-Hermitian topological system where we think about not energy conserving matter. And the second is a delicate topological system. That is a name that we introduced recently, and it refers to systems where not only the empty but also the occupied states, sorry, where not only the occupied but also the empty states matter. And in the third direction, I call this actual topological Anderson insulator. I want to show you another system where this distinction between occupied and empty states is actually not really relevant for the notion of topology. All right. So in showing you these three examples, I really want to give you a flavor of theory work. And these three examples, if you think of the lifetime of a theory project and the impact of it, they are really at the beginning. We've just been publishing these ideas, or some are under review. And so these ideas could potentially be irrelevant in the long run. If nobody finds any realization of this, they will die out. But of course, and I leave that maybe to your imagination, if you find the material realization of one of these ideas, then this has a larger impact. And the ultimate goal would, of course, be to find a use case where one of these new concepts would come to an application actually. So this is sort of the broader scheme in which I want you to think about the concrete problems that I'm going to talk about. And you can see basically how we work as theorists in this field, how things are based on some conceptual new insight. Let's start with these non-Hermitian point gap topological systems. So why would we want to think about non-hermiticity? Well, it is because energy is not always conserved in quantum systems or classical systems. And for instance, if you have a driven system or a lossy system where you have particle loss or energy loss, then the coherent part of the quantum evolution can actually be described by an effective Hamiltonian that is non-Hermitian, that doesn't have a real spectrum. And another aspect that we frequently encounter are Green's functions, single particle Green's functions, which contain complex self-energies. So they themselves are also not necessarily Hermitian objects. And of course, in classical systems, we are very, very familiar with dealing with non-Hermitian equations. There we have losses, resistors in electrical circuits, or other losses in mechanical systems and so forth. All right, so what happens when I have now a non-Hermitian Hamiltonian, quote unquote? Well, my band structure that I'm used to, it turns into a complex set of eigenvalues. So I'm a little bit bothered by this pointer situation, but here would be the band structure that we used to think about. Everything is lined up on the real axis. We can distinguish between occupied and empty states. And now everything spreads out in the complex plane. And we can have, of course, still this conventional separation of two bands, let's say, and the imaginary part you can think of as a lifetime of states physically. And then we say we have a line gap if we can separate extended number of states by a line. But that is a situation that can be transformed to this real axis, smoothly transformed basically to this real axis projection, and not much new is actually gained. The really interesting thing is if we have systems where eigenstates are agglomerated on a disk, basically around this a region where there are no eigenstates, and that's called a point gap system. And we can ask, is there any topologically interesting feature associated with systems that have such a spectrum with a point gap? Okay, going back to what is interesting in topology, I told you the boundary states are interesting because they are anomalous. And by anomalous, I mean they are only living because there is a topological special bulk system underneath them. So if I have a surface, for instance, that is the surface of a 3D TI that carries a single Dirac cone, and that thing is otherwise, it's not existing in a 2D system. So what anomalous states could we think of on the surface of a non-Hermitian 3D system. And there are two things that come to mind. One is exceptional points. And what I mean by that is a touching point of two energy bands, but these are now complex energy bands, so they touch both in real and imaginary part. So I have a different set of conditions than if I have just real eigenvalues or real energies. So that is one object, actually topological object that exists in 2D and is indeed, in principle, candidate for anomalous state. And another are much simpler, even Fermi points. What I call a Fermi point is, consider a 2D system and its spectrum. If I have a 2D system, a periodic crystal, I have a Brillouin zone, which is a torus in 2D, and I map this torus to the complex plane, then I get a double covering. So every point on the complex plane is covered by at least 2 points on the torus, otherwise there's no smooth map. And then in contrast, I could think of mapping an open part of the 2D plane to the complex plane, and then I would have the option of having a single covering. But that actually, this single covering situation that I show you on the right, that can never exist in a purely 2D periodic system. So the anomalous states, or the point of anomaly here is that both exceptional points as well as such Fermi points have to come in pairs in purely 2D systems. And I want to show you now how, when we go to topological 3D systems, we can have realizations where such anomalies appear on the surface of a 3D system. And here's one instance. I want to be very concrete about that. It's maybe the most technical part of my talk. I'm showing you just bluntly a Hamiltonian for a 3D topological insulator. The main thing you should maybe take away from that is that it's a 3D topological insulator. So it's that thing that has a Dirac cone on its surface. And so this will be the spectrum with the Dirac cone on the surface. And I actually want to tune it to a critical point where the bulk gap is closing and we have just like a 3D Dirac point in the bulk. And then I want to add to this model a Zeeman field. And actually I have here's a little complication. I want to basically put different G factors on different orbitals just to have a little bit more freedom later, but mostly think of a Zeeman field. And I want to put, now this is the main ingredient, a non-Hermitian term, a lossy term as well in this Hamiltonian. And this is a orbitally dependent, if you wish, not necessarily spin dependent, but orbitally dependent loss term. So somehow not the most trivial thing you could write. So now I want to tell you what happens to the spectrum of this thing as you put this loss term. So you have this 3D topological insulator, and in the bulk, these blue states are the energy eigenstates. And now that you put this loss term, they spread in the imaginary direction, and they open several of these point gaps along this the real axis. And in particular here in this critical situation, actually you get a really nice big point gap. Now you see I colored these point gaps already with different colors, and these colors correspond to different values of a 3D topological invariant. This is a 3D winding number. And maybe your question is now, has this any physical implication? So far I just did math. I just showed you a 3D TI plus some loss gives you some point gaps. And the physical implication is that if you look at the boundary of such a system, you actually get a bunch of boundary states, and now you have two options. Either you get this pattern of boundary states here. This is again a calculation of the spectrum in an open geometry, and this was formerly this point gap, or you get this pattern of boundary states, which has different symmetry. The reason why these things look so different, this was depending on this magnetic field term in the Hamiltonian, is that this is basically depicted as a map from the Brillouin zone, from the 2D surface Brillouin zone to this complex plane. Here this map is very regular, so the energy dispersion essentially of this band, of this surface band, is like kx plus iky. While here this is a little bit more irregular, and you can actually see this eightfold point here in the middle as an exceptional point on the surface. So you have two options, and actually we can show that with the surface manipulation, you can go from one option to the other. So they're both legitimate terminations of this non-Hermitian topological phase. Okay, so that's a novelty, these kind of topological boundary states in non-Hermitian phases. And it's always nice if you see something new to connect it to something that you know. And now I hope I can do that. If you know a little bit about vial semimetals, then I can hopefully make that connection for you and make this a little bit more intuitive for what happens here. So in a vial semimetal, you have these band touchings in the bulk. Let's say in the simplest case, we have just 2 vial nodes, 2 of these band touchings, 2 vial fermions. And what I want to invite you to do as a thought experiment, let's give a different lifetime to these 2 vial fermions. So this is still my real spectrum with some momentum resolution. These 2 vial fermions sit here. And I want to give them a different lifetime and think about the spectrum then in the complex plane of this Hamiltonian. And immediately you would realize, well, different lifetime puts them at different points in the imaginary direction. So the spectrum qualitatively would look like this. And now we have the point gap in this vial semimetal with different lifetimes. We have a point gap, so we are in good shape. And we actually also know another thing. If you know about vial semimetals, you know that these vial points are connected by Fermi arcs. And what happens now when I give them different lifetime, these Fermi arcs stretch across the point gap, and this vial semimetal is actually becoming my non-Hermitian topological insulator, or point gap topological state. I call it exceptional topological insulator with this point gap topology. So what you would see in ARPIS, for instance, in such a situation is that instead of a vial semimetal where you see 2 vial cones and a nice Fermi arc surface state, you would see just 1 vial cone. The other one has a short lifetime. And of course, that's not really a nice feature. So finding more transport type evidence for this would, of course, be a goal of future research. And also, of course, we have to see where in materials world would we find vial semimetals with such lifetime effects. So one option is to find them in F electron systems, where if you couple different orbitals to the F orbital, you might generate different lifetimes and the term that we kind of need for the Hamiltonian. And another option would be to look into systems where we couple to bosonic modes and get, for instance, by electron phonon coupling to a regime where, with orbital selective electron phonon coupling, we generate the terms that we need in the Hamiltonian. And if that's all a little bit tough and you're impatient as I am, you can do something classical. You can actually build an electric circuit and try to find exactly these effects in a classical system. And that's what we did, but no results on that yet. This circuit was just transferred from Zurich to Würzburg, so will be measured in detail in Würzburg. But yeah, soon we'll hopefully have some details on this. So I just have the pretty picture for that. All right, let me go back to my goal for you. So I now discussed one venue of going beyond the topological states that we've been looking at mostly in the last 15 years, and that is by going to non-Hermitian systems. Now I want to go to another theoretical idea, that is so-called delicate topology. And here we will see that the conduction band, the excited states, will also play an important role. And to take this point of view, I invite you to think about Wannier states. This is a very important concept, more recently got more important in thinking about topological states, topological matter. And so, just as a short sort of picture that you should have in mind, the Wannier states, they are a representation of the basis of the occupied bands in real space. So they are like little orbitals that are forming and represent, for instance, occupied bands in your crystal. And so these Wannier states in different topological systems or non-topological ones, they have characteristic properties. So in what we call a stable topological system, these Wannier states are actually not exponentially localizable. It's a very fundamental theorem. It's underlying the idea of topological quantum chemistry, for instance. So you have very spread, non-exponentially localized Wannier states in a stable topological system like a topological insulator. And this cannot be changed if you add more orbitals to your system. So this property is very stable, and that's why it's called stable. This should be contrasted with a topological trivial system where the Wannier states can be deformed into an atomic limit. So they can be shrunk basically to one atom site, and they're definitely always exponentially localizable. That's the other limit. And now there have been a bunch of new notions of topology that squeeze in between these two limits. One is that of fragile topology, which only concerns occupied bands. And there the statement is that the Wannier states are not exponentially localizable, so they look like these. But if I add a trivial band to these, or trivial states to these occupied subspace, then all of a sudden I can make them trivial, or I can make them exponentially localized. So this system depends very much on the set of orbitals that you work with. And now we found out there is yet another notion of Wannier state topology, and that is so-called delicate topology, where the Wannier states can be exponentially localized, but there is an obstruction from localizing them on a single unit cell. So this limit you cannot achieve by any adiabatic deformation. You always have them spread over at least two sites or two unit cells. And this feature, this topological feature of a band, can be annihilated by adding more Wannier orbitals to that band subspace, or, and that's why we thought that delicate is a good name, it can even be annihilated by adding orbitals to the unoccupied bands. So you might say, okay, well, this is almost completely useless. This is, very, very, even more fragile than fragile. So, but I'm going to, hope I'm going to try to convince you that there is some very interesting physics in that as well. So first of all, let me give you an example so that you have something in mind. What kind of system does show such a delicate topology? Where is delicacy? Let's go back to a very simple system that we've had on the first slide, the anomalous Hall effect or Chern insulator. And one view on the Chern insulator is, well, first of all, there is a so-called Chern number invariant. There's a topological invariant that gives you the Hall conductivity. But also, if you have a strip of Chern insulator, and you go through the states in the Brillouin zone along this strip, so you look at as a function of this still one conserved momentum, then the polarization of these states shifts by 1 unit. And that is really going hand in hand with this non-trivial Chern number. Now we can conceive a different system which has a mirror symmetry. This is kind of going to be important, a 2D system with a mirror symmetry. And in this system, there is in the Brillouin zone, there is now a mirror line here at 0 and at pi momentum. And I want to arrange it such that the Chern number on 1/2 of this Brillouin zone is quantized instead of the Chern number of the entire Brillouin zone. So I'm integrating some quantity, like the Hall conductivity contributed to the states in half of this Brillouin zone is 1. If I, by this mirror symmetry, would do the same computation on the other half, it would be turning out to be -1. And likewise, the polarization of such a system is going to 1 as you traverse half of this surface or edge Brillouin zone and goes back to 0. All right, so there's no Hall conductivity overall, but it has this funny Chern number in half of the system. Now, why is this stable? Why would that Hall conductivity of half of the states be stable? The reason is that we can actually compactify in some special situations, we can compactify this half of the Brillouin zone and think of it itself as a torus or as a Brillouin zone. And this is possible when we have a certain property of the orbitals involved that results from this mirror symmetry. So if you have a Hamiltonian that is written in a S and P orbital basis, it's a 2-band Hamiltonian, then by mirror symmetry along these mirror symmetric lines, the Hamiltonian has to be block off diagonal. The S and P cannot mix because of the opposite mirror eigenvalue. And then if it's a 2-band system, the eigenstates of the occupied and empty band, they are independent of this momentum. So along this line, the eigenstates are all constant. And that's why I can identify the eigenstates on this end of the Brillouin zone with those in the middle, while usually I identify them across the entire Brillouin zone. That's why Chern number on half of the Brillouin zone is well defined. If I add another band, and now it doesn't matter whether I add this band to conduction or the valence subspace, then I can mess up with this criterion and I can make the eigenstates momentum dependent along this line. And so this property, this delicacy, is lost when I add another band, and it doesn't matter whether I add this band to the conduction or valence subspace again. And this same principle, I just showed you the most intuitive example in 2D with Chern insulators, but the same principle holds in all kind of dimensions. So we can think of conditions to quantize topological invariance in half of the Brillouin zone, and it doesn't matter which invariant, you give me your favorite one, I'll construct you a situation where this happens. And so it's a kind of a quite broad concept. And it is related to this multicellularity that I'll now basically refer to. The fact that these Wannier centers cannot be localized on just a single unit cell. And the reason is, in this polarization case, you can see it, this polarization goes up to 1 and back to 0, but the fact that it goes basically from 0 to 1 means the eigenstate that is kind of moving with the polarization is actually moving by 1 unit cell. And so you cannot find Wannier states that are only localized on a single unit cell because the polarization has this property. So in short, my student draw this nicely on the blackboard. So the trivial orbitals, they're always possible to localize on just single unit cells or single sites, while these delicate topological systems, they have new kind of Wannier obstruction, which is multicellularity. Okay, let me give you another example of such a state, and that is a Hopf insulator. I don't want to formally introduce it because it's going to be a lot of formulas and so on, but I just want to tell you there exists a 2-band model in 3D, which has a set integer topological classification. It's a very well-known system. It has to do with a mathematical object, the Hopf vibration. This is a kind of Wikipedia cartoon of trying to show you what the Hopf vibration is, but it doesn't really matter for our discussion here. What matters is that there is this topological system. It's based on 2 bands. It's in 3D, and there's no symmetries that protect it. And we looked into detail. This is one example of a delicate topological system, and it's multicellular. And now the question is, do these multicellular delicate systems, do they show any surface anomalies, any boundary anomalies that are interesting? And here it's quite subtle at first, because what we found is that the surface is either non-Wannierizable, so you have no exponentially localized Wannier functions, or if you want to Wannierize it, then you are sort of breaking some symmetries, like this mirror symmetry in the previous case. So your Wannier functions are not exactly looking like they should. Okay. Now, all of these systems depend on the fact that you have only 2 bands, and you might wonder, well, how realistic is that? We always have a bunch of bands in condensed matter, right? I want to give you a perspective that, especially in these twistronic type of fields where we have very few subbands that are nearly flat, we actually have an excellent playground of looking for such topological states, because there a few subbands are kind of decoupled from the rest of the world in some sense. And so here's one proposal from us to realize not the delicate but fragile bands. If you use graphene and you decorate it with some d orbital atoms. And so that's just one example. One can also play with twistronics if one wants alternatively, but here's just a single graphene layer, just as an idea. And then this fragile topology, for instance, would manifest in corner modes. All right, that was multicellularity, delicacy, second part of my talk, second theoretical concept. Take a breath, there is one more. It's a short one though, I can promise you. And this is what I call actual Anderson insulators. And to tell you what I think is an actual Anderson topological insulator, I should first say what has been done in this field so far. And so that what people call a topological Anderson insulator is they take a topological insulator, like a quantum spin Hall effect type of state, and they put disorder on it, and then look what does the phase diagram look like, and it turns out that the phase, as you increase disorder, this going up here, the phase boundary turns towards the topological side, so the disorder helps you with the topological phase. And this has been seen beautifully actually in a photonic realization recently. But I think it's still sort of, if you look at this phase diagram, I find the role of disorder relatively disappointing, because the same topological phase that you can enter with disorder, you can also enter it if you can find, you know, a better parameter space for your non-disordered system. So I mean, this is great work, but I want to say that there should be something more intrinsic about disordered systems. And this is what I want to propose here. What I would call an actual topological Anderson insulator. This is a theoretical vision of a 3D system, which is completely localized in the bulk. There are no, it's a disorder localized. There are no delocalized states, but on its surface, it carries a Hall conductivity, and this Hall conductivity is opposite on two surfaces, let's say. However, the important thing about this system is that this Hall conductivity is obtained when I integrate over all states in that system. So usually you are thinking about a Hall effect, anomalous Hall effect, where you have two bands, and then there opens a band gap, and the occupied band gets a Chern number 1, Hall conductivity 1. The unoccupied one gets Chern number -1. Here, I want to propose a different strategy where you spatially, instead of energetically, separate states with Chern number 1 and -1. So you put them simply on opposite sides of your system, not separate them in energy. And then to still measure them, you could, for instance, bias the system, and in an out of equilibrium experiment, that would be actually an interesting endeavor to do. You could, since everything here is localized, you could kind of apply a gate voltage so that you only measure those on this side. So again, to contrast this with the conventional way of thinking of a boundary anomaly. So for instance, if you had a Hall conductivity induced on a TI Dirac cone, there you would have opposite Hall conductivities for excited and occupied bands. But here I want to really, there's no excited states. I really just separate the Hall anomaly basically just spatially, not energetically. And now I have to just tell you, how am I going to do that? Yeah, this is just a theory idea. Actually, I can do that by placing the 1-year orbitals of this Hopf insulator that I told you before. It's nicely connecting to this previous topic. So I have some really special, delicate, non-completely localizable 1-year orbitals. I just put them with this order in the bulk, and then I leave it there. And if I look at that system, so this is a kind of recent calculation from my student, it's actually stable. The system is now stable against perturbation. So you put some hopping here, and you can look at the Chern number, the surface Hall effect that you obtain by integrating over all the states near this surface. And it doesn't really matter exactly where you stop your integration or your measurement, because all these states in the bulk, by definition, don't contribute. That doesn't carry a Chern number. So this is a new paradigm for topological matter, where anomalies are spatially, not energetically separated. The anomalies are spatially separated. And this is also transferable to other topological phases. I can basically take not the Hall anomaly, but some other anomalous surface state and do the same thing. And of course, it fits this broader picture of using disorder as a resource for topological protection rather than a nuisance in a way. Okay, so now I finished that part of my talk where I wanted to lay out to you a bunch of different theoretical ideas, which are really sort of starting to solidify in our theorists' minds. And the next step would be to bring them to life with actual proposal in materials. And for that, I would like to quickly introduce to you some methodological developments that we do to actually bridge to experiments, because that's the important and ultimately relevant step. So three directions I would like to highlight that we do in my group. One is building ab initio type packages for doing transport calculations. So my postdoc Stepan Zirkin, he produced this one-year Berry package, which takes one-yearized ab initio band structures, and he managed to get a huge speed up with some new integration schemes against conventional ways of computing anomalous transport coefficients, both in the linear and nonlinear regimes. Basically can take his package and compute a lot of things that result from Berry curvature, Berry phases and the like. And what we try to do in the near future is to use basically large library of one-yearized tight binding models, which are starting to become available. So that's a collaboration with Masari and EPFL. So they have now a more automated way of actually generating the input data we need for such computations. And then we hope that we can do a high throughput run to see which materials, like vial semi-metals or so, which materials are prone to giving us giant anomalous transport responses. And that's, of course, something you can always use in many interesting applications, spintronics and so forth. Second thing is, if we go to systems where correlations and interactions are important, we need new tools to get to compute the ground states of these systems, or also time-dependent states. And what we do here is going to basically boost up Monte Carlo to a new level, and we use sort of new parameterizations of quantum states in terms of, for instance, neural networks or other many variable Monte Carlo parameterizations, and we use basically the neural network representing a quantum state to do computations on that. So a recent thing we did was to test this machinery on the pyrochlore lattice in 3D, where we computed a spin 1/2 Heisenberg model ground state, and we found, actually maybe slightly disappointing, that what was thought to be a quantum spin liquid ground state is definitely symmetry breaking. There's still some room for it to be a quantum spin liquid, but it's definitely not the most naive thing one would have thought there. And this basically now enables calculations, in particular in 3D, which are hard to do with any other method. And lastly, maybe bringing back one methodological development to topology, I would like to highlight an idea we have that's based on this principle of topological quantum chemistry. So topological quantum chemistry tries to compute topological invariants from Bloch state representations that you can easily get out of high throughput DFT calculations. However, this methodology is not able to capture some topological states which are interacting in nature. For instance, if you are familiar with that, the spin 1 Haldane phase would not be captured by this approach. And we are looking at extending this, which this is a single particle approach. So you think about Bloch Hamiltonian fundamentally, and what one can alternatively, this has been put forward by Sushan Zhang already a while ago, one can alternatively look at the Green's function. Now what we want to do is want to not look at the single particle Green's function, but we want to look at higher order Green's functions of such quantum systems and see whether we can read off certain aspects of topology of the quantum states from these higher order Green's functions instead of just the single particle ones. And these objects are of course experimentally in principle accessible, but also in a bit more extensive numerical calculations like extensions of DMFT or also CCSD and so on. They could be obtained in principle, and we could use that as input for large scale searches. All right, to close up my talk, I think it's time. So the journey that I wanted to take you on is the following. So I wanted to show you that we have in stock always this supply of new theoretical concepts, new physical principles that we formulate, and then based on these are really the foundations of our research. Based on these, we need to connect to real systems using, of course, some methodological, some numerical apparatus, and this could be either systems in bulk crystals. If we're lucky, nature is kind enough to give these concepts a a way to live, or we have to help a little bit and design quantum matter in such a way that such concepts can come to life. Or, of course, we can look at classical systems where completely different range of functionalities can be accessed. And this could be in photonics, this could be in mechanical systems or in electronic circuits, as I flashed briefly. And all of this, well, finally is supposed to feed to this bigger goal of building, new hardware foundations, new physical principles for electronics, neuromorphics, spintronics, quantum information devices, and so on. Okay, with that, I'm at the end of my talk, and I should not forget to thank my group and my collaborators for all the great work they put into, the lively exchanges and so on in what I presented. Good, thank you very much for your attention, and I'm open for questions.
So we have time for some questions. Let's see if there's any on the chat or in the audience. Yeah, Ronnie, you like to go?
Thank you, Titus, for this great talk. I've seen your work on delicate topology for the first time. So my question is, where's the Barry flux monopole in this half-Brière zone Chern number argument? Because if I ask for momentum parameter space and I ask where's the Barry flux monopole, I would have a hard time to put it somewhere, because when I have the whole Brière zone, it would just be placed out of the torus, right?
Mm-hmm.
So do you have a picture?
No, I think you have, yeah, that's right. So if you want to go to this picture, you probably have a monopole and an anti-monopole. And then by this mirror symmetry, there is a line on the torus where there is exactly no Barry flux. So the monopole and the anti-monopole, they have to cancel out in their field strengths, such that there's a line with no flux, or two lines actually on this. I think that's, so you could place them symmetrically, for instance, in the torus in certain two places opposite, I think, would be, yeah. Good.
Thank you.
Thanks. Maybe we can take a question from the audience and then we'll move to Prin. So if you could unmute, there's somebody asking in the chat. Yeah, he can.
Hello. Thank you for the talk. It's really interesting. I didn't understand. Sorry. Hello. Can you hear me?
Just a sec.
Maybe then we wait a moment. Yeah, I just wanted to say, then we go to Prin.
All right, excellent talk. I have a couple of quick questions, and one of them is, so you showed the one-year representation for getting the surface and then also linking with the bulk. I was wondering, do you ever introduce a discontinuity between the two when you try and stitch it together, or do you never stitch it together?
No, yeah, that's a good question. So what happens is that we put the same orbitals everywhere, but then because there's a surface, some of them are kind of cut off a little bit. Yeah. So if you put one, right on the surface, there like half of it is broken off, and then a very natural out of this actually the surface state appears. So we don't intentionally do anything special to the surface. We don't put intentionally a Chern insulator. It's just like by repeating that same orbital, and just by the fact that somewhere the system ends, we get this physical state.
And does that capture things like reconstruction that might happen at the surface?
Yeah, good question. So we haven't implicitly implemented any reconstruction, but this Chern property is a robust thing. So the fact that there's this Hall conductivity cannot be changed by any, actually, since in the particular case of the Hall conductivity, there's no symmetry protecting it. So whatever happens to that surface, I cannot remove that Hall effect. The only way to remove it would be to have a delocalized state that propagates through the entire bulk. So I said that bulk is localized, and so as long as that property is intact, there's no way of getting rid of this Hall conductivity on the surface.
One quick follow-up, if I may. Looking at Chair, if that's okay. So if you use the one-way representation that you construct, then could you calculate the electron-proton interactions then using the same representation, or would you need to think about?
No, I think, yeah, I mean, if you have a concrete crystal phonon model and so on, there's no problem, yeah. So these sort of putting this one-year state is a very theoretician kind of way of speaking, but what I can just as well give a Hamiltonian, a tight binding Hamiltonian, which is disordered, so it's not translation invariant, but I can give that Hamiltonian and then I can plug it into an electron phonon calculation. Should be no problem, yeah.
There, is the online working? Still no sound? Maybe, Amin, you could type your question and I would read it out.
Should I simply, I mean, is it the sound, the problem of the audio? Should I somehow add my sound here or so? No.
No, I don't.
I guess I shouldn't.
So,
I could just turn on the sound of my computer. Okay. Hi, can you hear me? No, can I hear you?
Amin has.
Yeah. Hello. Is it?
No, somehow not. Yeah, now it's getting, now I have that problem. Can you say the question?
Yeah, so I have some, like, I didn't understand many things, obviously, but I have a simple question. Since you were talking about, for example, when you introduced this non-Hermitian term to account for the imaginary part of the energy, and for example, you talked about the different lifetimes, it made me think if you can have the same formalism, for example, for bosonic systems, for example, for this photonic crystals, can you somehow develop this whole model for the photonic crystals? Because then you would have a bigger platform for experimental verifications and tuning the bands.
Yeah. Gonna mute you. Sorry, again, I have to mute you again, otherwise it's awful if I speak. So thank you very much. Yes, absolutely. So this is a good idea and absolutely possible. I mean, usually I think dissipation is a little bit harder to kind of, or it's a little bit less routine thing to engineer. Usually dissipation is just supposed to be reduced, not engineered. But if we think in this direction and try to engineer dissipation in a certain way, we can totally realize this physics in a photonic system while points in photonic systems have been shown. So this would be a good starting point if we then add a suitable Weil node specific dissipation. So yes, I think it's a very good idea. And do you grasp the key thing here? Yeah. Okay, sorry. I am assuming you're happy with this answer. If you're not,
You can maybe write in the chat. So
right.
I see a hand, maybe Niels. I'll bring the microphone.
Thanks so much, Titus. I think brilliant talk. I think it's a great example that even after 15 years of, this explosion in topological research, there's still plenty of new topological phases to be discovered. So I think this is really very remarkable. I was also impressed that you at the same time still have bandwidth to do all this method development to actually still find new or find materials to realize these new phases. So what I'm interested in is a little bit, where do you think these two worlds will meet? Mm-hmm. Because my feeling is that, initially this field started with mainly non-interacting phases where it was very easy and fast to find physical realizations, especially in the condensed matter systems. Mm-hmm. But now with many of these examples that you brought, it seems to me a little bit unclear whether we are ever going to find, via semi-metal that has a self-energy that is somehow different in two different wire nodes, for instance. Mm-hmm. So where do you think are maybe the low-hanging fruits where this can be realized, and what are the more challenging sort of projects?
So I think globally speaking that the 2D systems are probably closer to the low-hanging fruits because we have a lot of exciting instabilities already in 2D or quasi-2D systems that we could try to exfoliate, and then adding the degrees of tunability that we can have there with gating and with twisting and all of that I think there we can really have, you know, some realization. Of course, not specifically of these vial nodes because they are 3D in principle, but you know, we can think about 2D as well. So I think in 2D systems there's much to be discovered first. Yeah, and as far as 3D systems go, I think we really have to focus on systems where interactions are important, but low energy physics is not awfully complicated. I don't know, thinking of gadolinium, platinum, bismuth, or systems like that, where we can sort of, with some manipulation, we can, and you know, we can still kind of comprehend what's going on. Yeah. In 3D, I guess you're very quickly out of the realm of what you can understand when you add interactions. Yeah. So that would be my very global answer to your question. But you're right. I mean, there's a lot of challenge going ahead.
You have a question?
Okay, sure. Okay, yeah, thank you. It was a very, very interesting talk for me. Actually, even I'm the chemist, more chemist, material scientist. So I just have two short questions. The first one is for your 3D topological insulator, which you proposed. I think it's very fascinating. Do you have any idea about which type of structure or which type of materials which can fulfill the potential to realize such kind of effects or properties?
So I think, okay, so it's a little bit going back to the question of Niels. So my answer is likewise going back to that. I think so systems where you have, for instance, in high symmetry conditions, meeting points of bands which are, I don't know, quadratic or higher degeneracy are, for instance, a good starting point, because there you could start to break these symmetries that protect, for instance, a gap band touching in a controlled way with strain or things like that. And then you have low energy degrees of freedom that you can, you know, much easier work with. So that would be, I would go to these kind of systems, which we know a bunch, let's say, and then start to engineer a little bit. Yeah.
Do you see the possibility using the current graphene-based van der Waals structures?
Yeah.
Is there any possibility or potential to go to such direction?
Yes, I think also there. I mean, I guess the Moiré physics is really difficult because their interaction scales are sort of similar to the bandwidth, so maybe not going there directly, but you know, all the possibilities that are brought about by sandwiching also TMDs with graphenes or that is probably a good playground. Yeah.
Okay. The second question, going to at the end, you mentioned some topological quantum chemistry. With the green functional is a new method, right? You propose. I think this is also very interesting to me. Do you have any idea whether this kind of method can allow you to predict new chemistry, new reactions, new catalytic properties? Do you have any idea going to such direction?
Okay, that was not my go-to thing from my background. I think it would be really interesting to think about that, because of course, once we have these kind of Green's functions, we can think about, you know, the interaction with light and so on. Yeah, I'd be more than happy to discuss and explore that, but it's not the first thing where I have like already a list of to-do things on it. Yeah.
Great, thank you.
Oh, yeah, thank you very much for the nice talk. I had one question. You showed that when you introduced disorder, you could move from a trivial system to a topological system. So that sort of surprises me. So is that the same equivalent to temperature? When you increase temperature, you increase disorder. So does that mean as you increase the temperature, materials become more topological?
No, I think that is just quite fundamentally different, I'm afraid. So
why is that? Because the disorder, you didn't really describe the disorder, but disorder, of course, you can introduce by temperature disorder. So what's the difference?
So the difference is that the quantization that we think about, the quantization of the Hall conductivity also, that is going away. I mean, at least, you know, theoretically speaking, that is going away with increasing temperature. And well, okay. So let me give you another. No, let me try to answer differently. let's erase a little bit what I said.
Yes, well, then my second
To some
question-
extent, you can think of disordered systems. To some extent, you can think of disordered systems as actually completely, basically inert to temperature. You can think of them at infinite temperature once you have this disorder. So there's this whole field of many-body localization, which where effects that are really actually at infinite temperature are relevant, or in other words, the effects that are studied are robust to even infinite temperature, cranking up the temperature to infinity. But then the exponentially accurate quantization of a topological response function at high temperatures, that is a challenge in itself. So that is a different question. So if you want a quantum Hall effect, then it should really be quantum. Then you want to be at zero temperature.
Maybe I don't understand how you're parameterizing your disorder. Then you seem to be suggesting.
So it's just a zero. It's a zero temperature kind of. The Hamiltonian has this order by putting Wannier orbitals at different energies. That's the idea. So I just basically give an eigenstate, a Wannier eigenstate, and I put it at some energy. So it's like quench disorder in a crystal.
Okay, I don't really understand, but anyway. And the other thing I noticed that was absent from your talk was magnetism and spin. And it seems like, say, you talk about Anderson, the spin interactions are super important, and that can change completely the topological character. You can introduce magnetism, and then material which is trivial, like can become topological. Or you can change the character of the fermions from Dirac to Weyl. And I just wondered, why is it a magnetism?
Where is the spin? Where is the magnetism?
It seems to be super important.
Yes. So this is hidden indeed here. So many of these topological concepts also work for bosonic systems. Theorists say bosonic systems, but they mean mostly spin systems. And particularly useful for this are the methodological things that I presented. So both these neural network quantum states, where we looked at actually a spin system, they are a great way to do calculations there. But also, if we think about this topological quantum chemistry with these higher order Green's functions, this is actually made for topological mod insulators, and the topological phases of such topological mod insulators are essentially topological phases of spins. So spin liquid.
Mod insulators are usually collinear. I was thinking more of chiral magnetism, which I think is more relevant to these topological systems, since you talked about chirality. What about like chiral, where the today hot topic is chiral, non-collinear spin structures? And so I wondered, let's say you're talking about mostly non-magnetic systems. Can you imagine systems which are trivial, and once you introduce the magnetism, particularly chiral non-collinear spin textures, they would become topological? Is that possible? And is that ignored from your
No, no, it's not ignored. Yeah, I think I don't have to. I mean, one doesn't have to do much more. The chiral non-collinear magnetism already gives you a lot because it gives you the Barry phase for the electrons. So once you dope such systems, you're very quickly in theory land. You're very quickly in topological turf. Yeah. So so this is I think. I tried to, okay. You are right that all the examples that I gave here, they are very much from the spinless electronic sort of thought inspired, but much of this can actually be realized in spin textures. So notice, for instance, the Hopf insulator that I mentioned, that is an intrinsically time reversal symmetry breaking state, actually. So if I want to find a realization of that, I actually better look into systems like the ones you mentioned, where sort of the type of electronic states I envision here are coming.
Can I ask just one more question?
On a spin background.
One final quick question. Most of what you talked about was really atomic-like, and yet you did mention metamaterials. So I wondered, then you can create metamaterials with larger objects. There's a huge interest in quantum mechanics of large-scale objects. And so I wondered, which kind of metamaterials are you thinking about on what length scales? Let's say I'm thinking like, moire systems, can they become, when you introduce long-range potentials, can you imagine then systems which atomically are not topological, but you can imagine them on longer length scales that you might create artificially, they could become topological. What type of metamaterials are you really thinking about?
So if you want specifically quantum coherent things, then I would say two things are natural to consider. One are Josephson junction array kind of endpoint. I mean, that doesn't need to be like some manufactured Josephson junction. It could be, micro, like little superconducting islands.
You're talking like coherence through supercurrents. That's what you mean. Yeah.
Yes, so where the coherence comes through supercurrent. And another arena that I think is super exciting are these exciton polariton condensates and their coherent coupling, because this can now be quite well manufactured in sort of some micro pillars and so on. And I could, start to make micro pillar structures, let's say in 1D or 2D, couple them specifically, and then get some of these physics in a quantum coherent way. And now they have, exciton polariton condensation at room temperature even. So this could even be a quantum coherent room temperature effect.
Thank you.
Okay, thanks. I also have questions, but I think I will refrain. So for those of us who have questions, we can type in the chat. Titus is logged on also as a participant and probably can answer on the chat. So thank you for a great talk. And we will move to the next speaker.
Thank you very much again.